Can you all hear me? Right, okay. Then let's start. Right, okay. So today we are going to start hydrogen emission spectrum, the very important topic in the first unit. So last week, I think we discussed about spectrum, right? So last week we discussed about spectrum, and today we are going to discuss hydrogen emission spectrum. So before we go for the hydrogen emission spectrum, let's discuss the background. So remember, students, we talk about the spectrums, right? So what does mean by a spectrum? Simply, a spectrum means a set of electromagnetic radiations, right? So spectrum means, always remember, a set of electromagnetic radiations known as a spectrum, right? And I told you that spectrums mainly can be divided into two parts. And one more thing, why we are analyzing spectrum, why we should need this topic, what is the reason behind discussing this topic? Can you remember? Actually, we are under the topic location of electron. Location of electron. I told you that in order to find the location of electron, there are two ways. Number one is, actually we have to find the spectrums. By analyzing the spectrums, we can identify the location of an electron. And the next method is, we have to analyze the ionization energies. After discussing the spectrums, we can go for the ionization energies also, right? So spectrum means simply a set of electromagnetic radiations. So using set of electromagnetic radiations, how is it possible to find the location of an electron? I told you that according to the Niels Bohr theory, around the atomic nucleus, there are some certain energy levels. Electrons are moving, electrons are transferring in between energy levels, n equal 1, n equal 2, n equal 3. We know that one, when an electron is moving from low energy level to high energy level, that electron is absorbing the energy. That absorbed energy calculated as energy equal h nu equation. We have done enough calculations regarding this absorption energy or emission energy. And same thing, what will happen when the electron is moving from high energy level to low energy level, that will emit the energy. So that emitted energy also can be calculated using the E equal h nu equation, right? So you have to understand, students, when these electrons are moving in between energy levels, when these electrons are moving in between energy levels, they will absorb the energy, they will emit the energy. So we can collect those energies and we can arrange that one in a particular order. That will automatically will happen, right? According to the spectrums, actually that will automatically happen. All the energy radiations emitted by these electrons or absorbed by these electrons, we can gather that one, right? We can collect that one and we can analyze. Using that analysis, we can decide that these electrons are moving from this energy level to this energy level. Likewise, using the energy emitted or absorbed by these electrons when they are moving between energy levels, we can find the location of these electrons. That's why we are going to analyze spectrum. Spectrum means simply none other than a set of electromagnetic radiations emitted or absorbed by electrons when they are transferring in between energy levels, right? Actually, finally, the final summary of discussing the spectrum is we can prove, right? Final summary is we can prove Bohr's theory is correct. මේ spectrum analysis කියලා කියන්නේ තනිකරම අර Neil Bohr කියපු වාදය, right? We are going to prove the Niels Bohr theory. What is the main concept in Niels Bohr theory? Energy levels, right? He said that his main postulate is around the atomic nucleus there are energy levels, path. Nucleus එක වටේ energy levels කියලා path වගේක් තියෙනවා. එහෙම එකපාරට කිව්වට පිළිගන්න බෑනේ. නේද? එතකොට එයා කියනවා මෙහෙම energy levels කියලා path වගේක් තියෙනවා. He says that energy levels are there around the atomic nucleus. So electrons are located in these energy levels. We are going to prove that energy level concept using this spectrum. Our main topic is hydrogen emission spectrum. But before we go for the hydrogen emission spectrum, we have to analyze what? Atomic absorption spectrum and atomic emission spectrum. I'm going to discuss two practicals with you today. And these two practicals are really easy. If you can understand these two practicals, don't worry, I'll come to that point later. If you can understand these two practicals, I know that definitely you will understand. And hydrogen emission spectrum will be nothing for you, right? Most of the students are panic about the hydrogen emission spectrum, but I think there is no use of being panic of that one. Actually, that is very easy. Last year examination term paper, A-level examination paper, first MCQ is regarding the hydrogen emission spectrum. Very first MCQ. If you analyze the 2022 A-level paper, the very first MCQ is made from the hydrogen emission spectrum. Students, that question is really easy, right? Really easy. Anyone can do that one. So definitely you can do that one, right? Now, let's go for the classification again that we learned regarding the spectrum. So spectrums, the plural term is spectra. Anyway, I'll use here spectrum. Spectrums can be divided into two parts. Can you remember what are the two parts? I told you that the first one is continuous spectrum. Continuous spectrum. And the second part is discontinuous. Discontinuous. We can say that discrete. If not, I can tell line. there are some synonyms we can use for the discontinuous. Remember, students, spectrums can be divided into two parts: continuous spectrum and discontinuous spectrum, or we can tell discontinuous or discrete or line spectrum. Understood? Continuous spectrums can be divided into these two main parts. And continuous spectrum means if I consider a particular wavelength range or frequency range, in that particular frequency range or wavelength range, all the energy radiations are included. For example, look at this one, will you? The main example that we took is what? Electromagnetic radiations that we discussed in the last week class. Neither. So when I'm considering the electromagnetic radiation, for example, I'm going to take 10 gigahertz, 10 gigahertz and 100 gigahertz. This is not electromagnetic radiation range, but I'm taking a particular frequency range. In this particular frequency range, we have all the energy radiations. All the energy radiations are included, right? All the energy radiations are included. In this particular frequency range, all the energy radiations are included. Nothing missed. All of them are there. Correct? All of the energy radiations are included in between this frequency range. But when I'm considering the discontinuous spectrum, right? When I'm considering the discontinuous spectrum, I'm going to consider the same frequency range, 10 gigahertz and 100 gigahertz. So in this particular range, we have only few energy radiations only. We have only few energy radiations, right? Under the discontinuous spectrum, in a particular frequency range or in a particular wavelength range, we have only few amount of energy radiations. අපි මොකක් හරි මෙන්න මේ නිශ්චිත පරාසයක් ගත්තොත් frequency, right? If we consider a frequency, a certain frequency range, only few amount of energy radiations will be there. So what happened to the other radiations? That's what we are going to learn. That's what we are going to learn. In the continuous spectrum, we don't have to discuss anything. Why? In this particular frequency range, I told you all the energy radiations are included. All the wavelengths, all the frequencies are included. So therefore, no use of discussing this one. So our topic should be discontinuous spectrum. Exactly. In chemistry, we are going to analyze discontinuous one. In continuous one, we have nothing to analyze. Neither. We have nothing to analyze because all the energy radiations are included. In the discontinuous spectrum, we are going to analyze why few amount of energy radiations remain and what happened to the remaining radiations, those are missing. මේක ඉතුරු වෙලා තියෙන්නේ මෙච්චරයි ගොඩක් ඒවා අයින් වෙලා ඒවට මොකද උනේ? We are going to find out what happened to the missing energy radiations. So that's what we are going to do under the discontinuous spectrum. So hereafter, in our syllabus, we are not going to discuss continuous spectrum, but we have to discuss about the discontinuous spectrum, right? Under the discontinuous spectrum, again, this discontinuous spectrum can be divided into two parts. Okay, remember, keep in your mind, discontinuous spectrum can be divided into two parts. Number one is atomic absorption spectrum, or atomic absorption spectrum. Number two, atomic emission spectrum. Atomic emission spectrum, right? And now only we are coming to our topic. Under the atomic emission spectrum, we are going to analyze hydrogen emission spectrum. Very, very, very easy, right? Very easy. Now today you can confirm 1 mark in your A-level chemistry paper, because if you are given MCQ regarding hydrogen emission spectrum, you can confirm that one very easy. Let's discuss what happened there, right? So hydrogen emission spectrum. So this is the classification of spectrum, right? Spectrums can be divided into two parts. Number one, continuous spectrum. Number two, discontinuous. What are the synonyms for the discontinuous? Discrete or line spectrum. Study now, right? We don't have time to study these things again, right? Now study. Listen to the what I'm teaching here and everything what grab and put that in your mind. That's enough. Study now. We don't have to waste our time. Later we can discuss some questions, past paper questions. We can do them, right? So what are the classification? What is the classification? Spectrum can be divided into two parts: continuous and discontinuous discrete or line spectrum. And discontinuous spectrum can be divided into two parts: atomic absorption spectrum, atomic emission spectrum. And under the atomic emission spectrum, we are going to specifically learn hydrogen emission spectrum. So this is the classification of the spectrum. And I think last week I explained what does mean by, I gave you the note, what is continuous spectrum and what is discontinuous spectrum. I gave you the note, isn't it? Can anyone respond me? Yeah, I gave you, Lashmi. Okay. Right. So, ladies and gentlemen, now let's go for atomic absorption spectrum. I told you we are not going to discuss continuous spectrum, right? Because we don't have anything to discuss there. We don't have anything to discuss there because that's a continuous spectrum. All the energy radiations are included. But we have to analyze discontinuous spectrum. Why? Why some of the energy radiations are missing? From that one, what is the conclusion we can get? How we can find the location of electron using the spectrum, right? Someone asks you, if someone asks you, what is hydrogen emission spectrum and why you are analyzing spectrum, your answer should be, we are going to analyze the location of an electron. Ask this one from your friend, one of your friend, right? Some of your school teachers, right? They don't know the answer. Remember, the answer should be, our main purpose is to find the location of electron. Sir, Neil Bohr said that location of electron is energy levels. Electrons are what existing in the energy levels. No. We are going to prove that one. We are going to prove that one using the spectrum, right? In the ionization energies, we are going to a separate path, right? Ionization energy, analyzing ionization energies, little bit interesting than this one. Why? We have learned only about the energy levels. Hereafter, we are going to learn sub-energy levels, orbitals, how many orbitals are there, how many sub-energy levels are there. Now the first unit is becoming more interesting, right? You have learned the basic stuffs like electrons, protons, neutrons, what are the atomic models and everything you learn, right? Isotopes. So those things you learn. Now only we are going for the new interesting topics: ionization energy, right? Electron configuration. This is not the electron configuration. The different type of electron configuration you are going to learn. Quantum numbers, right? And we are going to draw the periodic table in the whiteboard, and you're also drawing that one with me. We are going to analyze the periodic table. So many interesting things are to come, right? Okay. Now, ladies and gentlemen, our topic is atomic absorption spectrum. Let's go for the atomic absorption spectrum. Right. In the tutorial, turn to the page number. So these are the things actually we discussed in the last week class. Okay, we discussed this one. Now let's go for the page number 30. Turn to the page number 32 in the tutorial. Turn to the page number 32 in the tutorial. In the page number 32, I have given you the topic atomic absorption spectrum. Right. Students, I need a help from you. The help means actually you must do this one. After today's class, you have to give me a feedback about today's class. After today's class, after the end of the today's class, you have to give me a feedback, and you have to put that one in the WhatsApp group, whether it is good or bad, understood or didn't understand, whatever it is, good or bad, I don't care. You have to give a feedback after today's class. Okay, will you do that one after today's class? Can you do that one? Everyone, please respond. Okay, done, deal. Right. Right. Now we are going to discuss about atomic absorption spectrum. Students, keep that in your mind. Now we are going to discuss the hydrogen emission spectrum. Before I take you to the hydrogen emission spectrum, we are going to analyze atomic absorption spectrum. Keep this in your mind. This is very interesting and very easy. Most of the students and some of the teachers are thinking that emission spectrum, absorption spectrum, these are very difficult. But I don't think this is very difficult. This is really easy. The reason that they are telling this is very difficult is actually some of the students can't understand properly, and some of the teachers cannot explain this one properly until the students understand this one. My advice for you is, this is really easy, really interesting. First of all, listen to this one first of all. And when I'm explaining this one, you can ask your doubts. You can put your doubts in the chat box without any hesitation. After the explanation, I will answer for your doubts. Just think about, you can understand this one. Then also don't worry. Why? Because these two practicals are not mentioned in our syllabus, right? Because I am discussing this one for our knowledge, right? Because if I teach this one properly, you can easily understand the emission spectrum. The most of the teachers are doing this one in wrong way. They are directly taking you to the hydrogen emission spectrum without teaching this one. So most of the students can't understand the emission spectrum. So therefore, we are going to discuss two practicals. After discussing these two practicals, everything will be very smooth. Understood? If you can't understand this one, don't worry. That is not actually affecting for the examination, right? The understanding point will be hydrogen emission spectrum, right? So first of all, I'm very sure about you that you can understand this one, right? Okay. Very easy, right? Very easy. Atomic absorption spectrum. So first of all, I'm going to draw a diagram. You also have to do this, draw this diagram in the page number 32. After the atomic absorption spectrum, I have given you space and paragraph. End of the page, I have given you small space. At there, you have to draw this diagram, okay? And I'll explain you one by one. Right. The diagram is look like this. Very easy, right? We have a hot tungsten filament. Do you know what does mean by filament, right? Filament means actually in a light bulb, we have a kind of a spring like a filament. So that is filament. Okay. So this is white hot tungsten filament. And look at this one. Here we have a chamber. Right? And here we have a prism. So do we have to do this practical? As a LO student, you must do this one actually. But in school, actually, we don't have this much of instruments to do the practicals, right? If your school is very rich, then they can conduct this practical. Ask from your school teacher whether you could possibly do this one. සල්ලිකාර ඉස්කෝලේ ඇතිනේ. ඒගොල්ලන්ට කරන්න පුළුවන් මේක. ප්‍රින්සිපල්ට ගිහලා කියන්න, ටීචර්ස්ලාට ගිහලා කියන්න මේ ප්‍රැක්ටිකල් එක කරන්න ඕනේ එතකොට කරයි. Right. So these are the four main components we have, right? Let's finish this one very smoothly, very easy. So here we have a sensitive screen. Students, through this white hot tungsten filament, some of the energy radiations are emitting. energy radiations are emitted by this white hot tungsten filament, right? Just imagine this is a light bulb. So using that light bulb, we can get the light. Light is an energy. We can see the light as an energy, visible light. In this way, this is a continuous spectrum. Right? Energy radiations emitted by the white hot tungsten filament. So this is a chamber. Inside this chamber, we have hydrogen atoms. I will write down here excited hydrogen atoms. Yeah, put your doubts in the chat box. I will answer for them, right? First of all, I'll explain this one. Excited hydrogen atoms. Prism, sensitive screen. Right. My question is, tell me all of you, the energy radiations emitted by this white hot tungsten filament, is that continuous spectrum or discontinuous spectrum? What do you think? I think I told you the answer. Is it discontinuous or continuous? The energy radiations emitted by this white hot tungsten filament, is that continuous or discontinuous? What do you think? Continuous. Very good. Continuous. Very good. You can understand it because this is light. Light means visible light. Visible light is a component of the electromagnetic radiation. We learned that one electromagnetic radiation is a continuous spectrum. So therefore, we can consider this is, no doubt about it, this is actually continuous. Continuous radiation beam. Yeah, let's write down a continuous radiation beam, right? Okay. Now, from the chamber, now some of the energy radiations are emitting in this. Another set of energy radiations. And here we can gather that one in this way. Right. Inside the chamber, we have hydrogen molecules. And hydrogen molecules going to separate into hydrogen atoms. And then hydrogen atoms can absorb the energy, right? Okay, now this is the diagram we have to draw under the practical. Now students, try to understand what's happening here. I'm going to explain like to a baby, right? Very easy. Now what will happen? Students, we have used here white hot tungsten filament. It should not be always white hot tungsten filament. It can be, if you want, you can take a light bulb, doesn't matter, right? So I have used white hot tungsten filament because we don't have any covering. So we can take the direct electromagnetic radiations through this white hot tungsten filament, right? And then we know that one from the light bulb, energy radiations are emitting as light. So I have collected those energy radiations. Remember, since the visible light is a component of the electromagnetic radiation, this is a continuous radiation beam. මේ මතක තියාගන්න මේක continuous. This is continuous energy radiation beam. What does mean by continuous energy radiation beam? All the energy radiations are included in that frequency range. So we have a particular frequency range for the visible light. Can you remember last week I gave you homework to find out what are the visible frequencies and the wavelength corresponding to the each color in the visible light. So that means you know that there is a particular frequency range and the wavelength range. Continuous energy radiation beam means all the energy radiations are included in this visible light region. Okay, done. Now what happened? Filament is emitting some energy radiations. All the energy radiations are included. Continuous radiation beam. Students, remember, now inside the chamber, I have inserted hydrogen gas molecules. Mama make hydrogen vayu. I have inserted hydrogen gas molecules inside this chamber. What do you think? Our topic is atomic absorption spectrum. Atomic means atom. Which atom? Hydrogen atom. Because we have used here hydrogen. Hydrogen gas is colliding with these energy radiations and forming hydrogen atoms. And these hydrogen atoms are absorption. Look at this term. This term is absorption. Students, me atomic, that means hydrogen atom. Absorption. Absorption means absorbing. Absorbing what? Absorbing what? Absorbing the energy radiations emitted by this white hot tungsten filament. This tungsten filament, this filament is releasing energy as light. Now that energy going through this chamber, inside the chamber we have hydrogen atoms. These hydrogen atoms are absorbing the energy. These hydrogen atoms are absorbing the energy. Now quickly go for the Niels Bohr postulates. Under the third postulates, I told you that when the electrons are moving for the high energy levels, they will absorb the energy. That means these hydrogen atoms are absorbing the energy and going for which energy levels? Low energy levels or high energy levels? High energy levels. Understood? High energy levels. These electrons are moving for the high energy levels, Baba. Understood? These electrons are moving for the high energy levels. Right? Now, what will happen? This continuous energy radiation beam is going through the chamber. Now, some of the energy radiations are absorbed by the hydrogen atoms. Now, you can see from the other side, some kind of emergent radiations, right? So we can name this one as emergent radiations. Emergent means actually emitted radiations. Emergent radiation. After absorbing some of the energy radiations by this hydrogen, after absorbing some of the hydrogen radiations emitted by this white tungsten filament, some emergent radiations, emitted radiations are coming through the other side. Now my question is, tell me, think about this one properly and tell me, these emergent energy radiations, these emergent radiations, are they discontinuous or continuous? Let's see your answer. Now tell me, these energy radiations, are they continuous or discontinuous? Yeah, Lakshmi, correct. Correct. Yeah, very good. Understood. Most of you can understand. Very good. So remember, these emergent radiations are discontinuous. Why? Some of the energy radiations are absorbed by the hydrogen atom. May continuous may discontinuous. The reason behind that one is most of the hydrogen atoms in the chamber is absorbing some of the radiations from this white tungsten filament that emitted radiations and releasing some of the energy radiations. Those are emergent radiations. We can see that one as a discontinuous spectrum. And then this discontinuous spectrum is going through a prism, and we can analyze that emergent radiations, the filtered radiation. The correct term should be filtered energy radiations. These filtered energy radiations can be analyzed through a sensitive screen. We learned that one from the cathode ray experiment. In order to see the radiations, we need to have a sensitive screen. Through this sensitive screen, we can analyze some of the energy radiations are emitted. Do you know that one? Now, this is the sensitive screen. Now, if I take the sensitive screen in this way, screen is look like this, right? And I'm going to take that screen. In that screen, I can see some lines like this. I can see some lines like this, okay? Shall I draw that one? That sensitive screen is like this. This is the screen. That screen is look like this. This is the screen. That sensitive screen is look like this. In this sensitive screen, we can see dark lines in bright background. Dark lines in bright background. Baba me, can anyone say that? Can anyone say that? Why dark lines in the bright background? We have a sensitive screen. Energy radiations are emitted and we can analyze this energy radiation through this sensitive screen. Finally, you can see that dark lines in bright background. Can anyone tell me what does mean by these dark lines and bright background? මොකද්ද මේ dark lines වලින් represent කරන්නේ සහ මොකද්ද මේ bright background එකෙන් represent කරන්නේ? What does mean by dark lines and what does mean by bright background? What do you think? What is your opinion? Very good. Opeshani, correct. Very good. Right? Students, make dark lines. Can you remember? In the sensitive screen, that is sensitive for the energy radiations, if you see dark spots there, dark spot, remember energy radiations are missing. Some of the energy radiations are missing. In this sensitive screen, I can see, according to the diagram I have drawn here, 4 lines are obtained, 4 dark lines. That means 4 energy radiations are missing according to this diagram. So what is that bright background? Bright background, I told you that one, when energy radiations are colliding with the sensitive screen is bright. The sensitive screen is glowing with a bright color, right? So therefore, the remaining space is completely filled with the energy radiations. But 4 lines are missing. Is this continuous? No. That's why we consider atomic absorption spectrum under the discontinuous spectrum. Dark lines are representing that some of the energy radiations are missing. So if all the energy radiations are included there, this sensitive screen should be completely bright. Sampurnema sensitive screen එක දිලිසි තියෙන්න ඕනේ බබා. But it's not like that. Some of the energy radiations are missing, so therefore we can see that some energy radiations are missing. Dark lines is missing. My next question, what happened to these 4 energy radiations? What happened to these dark lines? What happened to these energy radiations? What do you think? As you think? Absorbed by who? Hydrogen atoms. That's why we call this one as atomic absorption spectrum. Atomic absorption spectrum. Understood? Right? These dark lines are representing some of the energy radiations are absorbed by hydrogen atom. That's why we call this one as atomic absorption spectrum. Nice, isn't it? By analyzing, we can tell that definitely these electrons have absorbed the energy. The electrons in the hydrogen atom absorb the energy and they move to the high energy levels. High energy levels. Understood? Sir, in the hydrogen atom, we have only 1 electron. So therefore, there should be only 1 line. No. We have lot of hydrogen atoms in the chamber, not only 1 hydrogen atom. There are so many lines. So these are the possibilities. Understood? Right. First of all, now tell me. So this is the practical. That's all. That's all. Right? Filament emitted energy radiations. That energy radiations absorbed by the hydrogen atom in the chamber. And the release, that means the remaining radiations, the filtered radiations emitted by the other side from the chamber. and we analyze that one through a prism, and we can see this kind of dark lines in bright background. Just imagine, students, just imagine we don't have this chamber. We don't have this chamber and prism, nothing is there. We have only that white tungsten filament and the sensitive screen. What will happen? We can see nicely bright sensitive screen because all the energy radiations are there. All the energy radiations are there. So not hydrogen atoms are there. So therefore no dark lines. No one absorbs the energy. So therefore we can see nicely bright color sensitive screen. But here some of the dark lines are there because hydrogen absorbs the energy. Right. Now, first of all tell me, ladies and gentlemen, did you understand the experiment? Raise your hand who understood this experiment, that my explanation. Let's see how many of you understood this one. Very easy. Nothing is there. Anything is not difficult. In the session, there are 32 people. Only 27 people raise your hand. And what happened to the other remaining 5? Let's see. Who is that? Nuha, Sandeep, Tarushi. Do you have any doubts? Okay, 29 raised hand. What about Amshi, Sandeep? Right, okay. Now, if you have any doubts, let me know. Let's see. You have to join for the session at correct time, Amshi, okay? But okay, it's okay, fine. We can you can go through the recording. Right, now let's go for the doubts you have. Put your doubts in the chat box. Lakshmi asked the sir, so why can't we use an ordinary bulb instead of the filament? Remember, Lakshmi, we are using a covering. That means kind of a glass cover is there. So therefore, we cannot see the energy. We cannot take the continuous energy radiation properly. That's why we are using filament. Okay. And Sinetma, that means we can identify what radiations are survived and what radiations are absorbed. Yeah, exactly. That's what we are going to do. That. And the electrons move high energy level to chamber and prism. The electrons move to high energy level in chamber and prism. No. Electrons are moving to the high energy level only in the chamber, right? Because hydrogen atoms are only in the chamber, not in the prism, right? So from what kind of a material the chamber is made up of? Glass. Glass is the material. So can you do the question number 45, 48 question in the tutorial? I will discuss that one later, okay? I'll tell you what will happen to that one. Homework discussion. So why do we use prism? So we can use a prism because in order to get a kind of a separated energy radiations. You can gap prism. Understood? We can see that one energy radiations properly by keeping a space, by keeping a gap through a prism. That's why we are going to keep a prism. Understood? So try to understand, students. These dark lines are representing some of the energy radiations absorbed by the hydrogen atom. So can you please tell me what are the purpose of using each of these apparatus? Very easy. I told you why we are using tungsten filament in order to get the energy radiations. Why we are using chamber in order to include the hydrogen atoms, because we are analyzing the absorption spectrum. We need the hydrogen atoms to include in the chamber. That's why we need the chamber. Why we are using prism? Because we need to separate these energy radiations. We have to keep a gap. And why we are using sensitive screen? The use of sensitive screen is we need to see the energy radiations properly. Very easy. Can we use concave lens? Yeah, we can use concave lens also. Doesn't matter. Where you are going to use concave lens? Why you are using concave lens? To what purpose? So how the spectrum? Instead of prism, we can use concave lens. Doesn't matter. Yeah. So how the spectrum is made of hydrogen atoms? I told you that inside the chamber, cellular, inside the chamber we have hydrogen atoms. Those energy absorbed by the hydrogen atom. Why we are using particularly hydrogen atom? Why in the syllabus they have given only hydrogen emission spectrum. We could have analyzed helium emission spectrum, lithium emission spectrum. Remember, hydrogen is the simplest atom we have. Only one electron is there. This one electron spectrum is also complicated. Just imagine we are going to analyze lithium, sodium spectrum. How is it complicated, right? Hydrogen emission spectrum is also complicated. But if we analyze sodium like element, there are 11 electrons. So you have to analyze the spectrum of these 11 electrons. That's very difficult. That's why we are particularly using hydrogen atom. Is it possible to use other gases? No. We are analyzing only the hydrogen emission spectrum because if you use other gases, that will be very difficult to analyze, right? Instead of prism. That's what excited atom. Excited hydrogen atom means, just imagine excited. Excited means hydrogen atoms have moved for the high energy levels. So therefore, that hydrogen atom has gained the energy that is excited, right? Ground state, excited state. Ground state, excited state. In excited state, energy is high. In ground state, energy is low. Very easy, right? And then electrons move to high energy level in chamber and prism. Electrons move in high energy level only in the chamber because hydrogen atoms included in the chamber. Why prism? In the prism, we don't have hydrogen atoms, right? Prism is used to analyze these energy radiations. We need to keep a gap between the radiations. These energy radiations are separated by keeping a gap. That's why we are using a prism. But here, inside the chamber only, hydrogen atoms are there. Therefore, hydrogen atoms are moving for the high energy levels inside the chamber. That means inside the chamber only we have hydrogen atoms. There is no gas in prism, right? Okay. Then how only few energy radiations are released? No. Don't misunderstand. Here also we have only 4. Okay, I'll draw in that way. Then if you will misunderstand that. Here also we have only 4, right? I will raise this too. Now okay, neither. Right. Here also we have 4, right? Nuha, now okay. So what is excited hydrogen atoms? Okay, now we'll explain that one. Excited hydrogen atom means energy is high. That hydrogen atoms have moved for the high energy level. So that is excited state. Ground state means low energy level. Excited state means high energy level. That electron has absorbed the energy and moved for the high energy level. So therefore, that electron in the high energy level is excited hydrogen. And remember, these emergent radiations are going through a prism, and you are getting the same amount of energy radiations through this prism, and we can analyze that one through a sensitive screen. Is this difficult? No, right? Any doubts? Quickly. Any doubts? Anything? Wow, you are very talented, Nick. Okay, very good. Okay, nice. That means all of you understood me. Then in the page number 32, before write the paragraph, first of all, draw this diagram, because this is the practical I want to diagram. I want to explain this one. So quickly draw this one. Don't waste time, quickly. Yeah. And others, if you have any doubts, put your doubts in the chat box. I'll explain that. So what the spectrum is made up of whole beam? No. So that spectrum is made up of that whole beam. No. Spectrum is made up only 4. Because remember, 4 energy radiations are absorbed. According to my diagram, 4 energy radiations are absorbed by hydrogen atoms. So therefore, all the energy radiations are not equal. Whole beam. That is wrong. So there is only 1 electron in hydrogen. So we should only have 1 dark line. But as the many hydrogen chamber, we have dark lines as the electrons move from energy levels by absorbing. Is that so? Yeah, Peshani. I explain you that one. One of you can argue with me, sir. Hydrogen is containing only 1 electron. So therefore, we should have only 1 dark line. Sir. But remember, in the chamber, how many hydrogen atoms are there? So here, we can have so many possibilities because number of hydrogen atoms are there. So how many electrons are there? We can't even count. So many hydrogen atoms are there. So these are the possibilities. So we can continue this one up to many times. Okay, so this is only one part, few parts. Operation, yeah, that is the way. We can draw this one. Yeah, one hydrogen absorb one radiation means, yeah, one possibility, but there can be so many possibilities, right? That means, and at one time, one electron transition, that means one radiation. In another time, there can be another transition. Just imagine hydrogen is moving from first energy level to second energy level, right? At the initial state, that means at t equals 0, hydrogen is electron in the hydrogen atom is moving from the first energy level to second energy. After some time, that electron is moving for the third energy. So therefore, at one time, one energy radiation. Okay, done with drawings. Shall I erase this one? I want to erase this one. Okay, doesn't matter. Take your time. Students, I see that some of you are actually collecting the recordings. Huh? I know that one, but don't do that one, because after school started and after some time, your workload is very heavy. You have to do a lot of works. Therefore, daily attend for the live classes and cover that part, cover that unit in that class in that 3 hours. You don't have time to watch the recording. In case if you can't attend for that one, only you have to go for the recording. Understood? So therefore, please don't do that one. So that is big disadvantage for you, right? Don't depend on the recording. That's a very bad habit. If it is an urgent case, in some cases, if you can't attend for the session, doesn't matter, but always try to attend for the live session. Yeah, dark lines in the bright background means the missing radiations. Dark lines are representing missing radiations. Bright background is representing what? The remaining radiations. Actually, these black color lines or dark lines are missing radiations. Don't think that these things are missing radiations. Okay, these are the emergent radiations. So actually here we have only 4. Here we should have many, right? Actually the diagram should be like this. It means we can draw many radiations here, and here also we can draw many radiations. Yeah, drawing that way. Don't think that these are missing radiations. I also have drawn here 4 lines. Actually that should be, these are emergent radiations. There can be many radiations. These 4 lines are representing missing radiations. So therefore, these are not missing radiations. These green color lines are not missing radiations, right? So there should be many radiations that emitting from the coming through the prism. Yeah, that 4 lines, these 4 lines are representing the missing radiations. The 4 dark lines, these 4 dark lines are representing the missing radiations, but these radiations are filtered radiations. After absorbing some radiations, these are the filtered radiations, right? So there should be more radiations as filtered radiations. So that bright background is representing those filtered radiations, right? These green color radiations are in the bright background. Understood? These green color radiations are in the bright background. Don't make a count here. There should be many radiations, right? We cannot draw everything here. If not, that will be if I draw that one, that will be very ugly. So therefore, draw few diagram made radiations. That's enough. Okay. Quickly complete this one. Done. Okay. Right. I'm going to erase this one. Right. Now write down in the page number 32. I have given you space. After the topic atomic absorption spectrum, you are given some rules to write down at there. Quickly write down. The absorption spectrum, write down quickly. The absorption spectrum of an element can be obtained by analyzing the radiations emitted by a beam of light whose wavelength / frequency is continuously spreaded in a certain range. Quickly write down this one with me. The absorption spectrum of an element can be obtained by analyzing the radiations emitted by a beam of light whose wavelength or frequency is continuously spread in a certain range, and it was passed through it was passed through a chamber with hydrogen atoms. We are using a chamber with hydrogen atoms, right? So in the page number 32, given space, quickly write down this one. This is the experiment actually we conducted. And then they have given, let's consider how to obtain the atomic emission spectrum of atomic hydrogen. To do this, wavelengths emitted by a wide tungsten filament must be transmitted over a wide range of continuous radiation beam through a chamber with excited hydrogen atoms, and the resulting radiation is transmitted through a prism to a sensitive screen. So that's what we have done. Done, eh? Right. Okay, quickly go for the page number 33. Quickly go for the page number 33. Tagalen, pituanga tistunada. Nagi varakkalada. Marmalezi, very easy. Page number 33. Again, you are given some space right down there. This absorption spectrum, write down this absorption spectrum in the page number 33. Yeah, this absorption spectrum is a line spectrum, right? That means you can write down in bracket discontinuous. Yeah, as I mentioned you, discontinuous, because some of the energy radiations are missing. Either discontinuous. This absorption spectrum is a line spectrum with, this is very important, use a color pen, red color pen, dark lines on a bright background. Dark lines on a bright background. Dark lines on a bright background. Dark lines are representing energy radiations. Dark lines are representing energy radiations absorbed by hydrogen atoms. Bright background is representing the remaining radiations filtered by the chamber. Right, okay, quickly. In the page number 33, this is very important. Dark lines on a bright background. Dark lines are representing the energy radiations absorbed by the hydrogen atoms. Dark lines are representing the energy radiations absorbed by the hydrogen atoms. And the bright background is representing the energy radiations filtered by the chamber. Quickly. Are we done? Okay, good. Right. Now I'm going to erase this one quickly. This absorption spectrum is a line spectrum with dark lines on a bright background. Dark lines are representing energy radiations absorbed by hydrogen atoms. Bright background is representing the remaining radiations filtered by chamber. Okay. Now look at this one. This is very interesting, Lamai. Okay, very interesting. Right. Now look at this one. Look at the diagram I'm drawing here. Right. N equal 1, first principal energy level. N equal 2, second principal energy level. N equal 3, third principal energy level. N equal 4, fourth principal energy level. N equal 5, fifth principal energy level. So as can you remember I told you that, right? So remember, this is the energy level diagram, right? I'm going to explain that spectrum you obtain in the sensitive screen using the energy level diagram. And let's draw the corresponding spectral line diagram also. What is that name, sir? Spectral line diagram. That means the lines that you obtain the sensitive screen. So that is known as spectral line diagram. Okay, nothing else. Line diagram. What are these two diagrams? These are the corresponding two diagrams of the atomic absorption spectrum. First one is energy level diagram and the second one is spectral line diagram. Now, can you remember I told you that in the spectral line diagram, we obtain 4 lines in this way. No one asked me that, sir, why that lines are approaching each other. I thought that one of you will ask that one, but no one did ask that. Okay, doesn't matter. I will ask the question and I will answer. Right? So these are the lines you obtain. Okay, dark lines on a bright background, right? On a bright background. Dark lines on a bright background. Right. Now, ladies and gentlemen, look at this one. Be careful. Huh? Look at this one. Absorption spectrum. I'm going to explain that one using the energy level diagram. Ultimate truth. We are going to learn that one. Sir, what is this line? Why these lines are approaching each other? How that lines are formed? Can you explain that one? So you said that, okay, energy radiations emitted by the filament absorbed by the hydrogen atoms and the emergent radiations went through the prism and we analyzed the emissions absorption spectrum. And we obtained 4 lines. These 4 lines are approaching each other and exactly what exactly these lines are representing. Students, remember, I told you this is absorption spectrum. Look at the first line from the right hand side. From the right hand side, this is the first line we obtain. This first line is representing the electron transition from the first principal energy level to the 5th principal energy level. Can you understand? May the electron transition from first one to 5th one is represented by this spectral line. Look at this one. I told you that electron in the first principal energy level is moving for the high energy level and they will absorb the energy. that energy is denoted as a line in the spectral line diagram. Understood? When the electron is moving from the first energy level to the fifth principal energy level, that will absorb the energy. That amount of absorbed energy is represented by this spectral line. This spectral line. Understood? Now, remember students, this is the electron transition form n equal 1 to n equal 5. This is the corresponding spectral line n equal 1 to n equal 5. Can you understand? Can you understand that one? Raise your hand who understood that quickly. Boruwada tosan depa. Hari? Attarama therunana vidara katusan. So what about to the other remaining 6 or 7? 6 people? 5 people? Do you have any doubts? Sir, can you repeat? Please repeat. Yeah, exactly. For sure. Definitely. I will repeat. Doesn't matter. If you can't understand anything, I will repeat. I can explain you this one 10 times, even 10 times. Doesn't matter. I want all of you to understand this one. Right? That's enough for me, right? And now look at this one. Very easy, nothing. Huh? Now, in the spectral line diagram, in the sensitive screen of the experiment that we discussed, according to that diagram, I told you that we had 4 lines. So these are the 4 lines actually that I got from that experiment, sensitive screen. Remember students, I told you that in that experiment, hydrogen atom absorbed the energy. Hydrogen atom absorbed the energy. That's why 4 lines, 4 spectral lines in the sensitive screen that you saw is missing. We know that according to the Niels Bohr diagram, when the electrons are moving for the high energy levels, they will absorb the energy. When the electrons are moving for the high energy levels, they will absorb the energy. This is the spectral line you obtain in the spectral line diagram, that corresponding to the electron transition from n equal 1 to n equal 5. Baba, this spectral line is representing the energy gap between n equal 1 and n equal 5. This line is representing the electron transition, the energy gap between n equal 1 and n equal 5. Now, look at the second line. Now, the second line is representing that electron is moving from the first principal energy level to fourth principal energy level. First one to fourth one. Understood? First one to fourth one. N equal 1 to n equal 4. Oh, I can write down. N equal 1 to n equal 4. Understood? N equal 1 to n equal 4. And this is n equal 1 to n equal 4. Can you understand? N equal 1 to n equal 4. Right. Now, third line. Third line is representing the electron transition from n equal 1 to n equal 3 in this way. Look at this one. N equal 1 to n equal 3. And this spectral line is representing the electron transition from n equal 1 to n equal 2. Understood? This is n equal 1 from n equal 1 to n equal 2. This is the electron transition from n equal 1 to n equal 3. This is n equal 1 to n equal 4. N equal 1 to n equal 3. N equal 1 to n equal 2. Can you understand what happened now? Can you understand? Then can you understand what happened? These 4 lines are representing when the one and only electron in the hydrogen atom, when it moving from first principal energy level to fifth principal energy level, you can see that one as a line in the spectral line diagram in this way. On the polygon line. When the same electron moving from another particular time, in the same electron moving from the first principal energy level to the fourth principal energy level, you can see this second spectral line in the spectral line diagram. When you go for the next electron transition, possible electron transition, n equal 1 to n equal 3, we can see the spectral line, corresponding spectral line in the spectral line diagram as n equal 1 to n equal 3. And the last one, n equal 1 to n equal 2. 1 to 2, that line can be seen in this way. Now your doubts. No. Mushab, there can be more than 4 because look at this one. The number of energy levels can be up to infinity. So therefore, we can have another line, another one. Likewise, we can continue that one. So for our study, for our analysis, actually we are using only 4 lines. Okay. So it's like energy levels are drawn vertically in spectral line diagram. No. Ambo, veradi. Senura. Remember, students, most of the students are misunderstood that these are energy levels. This is energy level diagram, right? This is the energy level diagram. But remember, this is spectral line diagram. In the spectral line diagram, there are no energy levels. Meva energy levels nemei. These are not energy levels. These are lines representing the corresponding electron transition, the energy gap between these two energy levels represented by this spectral line. These are not energy levels. These are not energy levels, right? So why the gaps vary? Yeah, I'll explain that one. Sir, does each lines represent individual hydrogen atom? Yeah, these are the possible electron transitions, right? Now again, you can tell that, sir, we have only 1 electron in hydrogen atom. So how we can possibly have 4 lines at the same time? Remember, these are not the 4 lines we obtain at the same time, 4 different times. And remember one more thing, there are so many hydrogen atoms. If one hydrogen atom is moving from first principal energy level to fifth one, the other one can move from n equal 1 to n equal 2. So there are possibilities. These are the all possibilities you can obtain. That's why I have drawn here. And one more thing, now one of you asked that, you have same doubt. I know that you all have same doubt. Sir, why the gap is decreasing? What is the reason that gap is decreasing? Students, look at this one. Very easy. Look at this one. If I see the energy of this line is 100 kilojoules, and this is the energy 1000 kilojoules. This is 1500, 1700. Yeah, let's consider 1800. And this is 1900 kilojoules. I told you that, look at this one. Now look at this one. In the energy level diagram, energy level gap is decreasing, right? Energy level gap is decreasing. So like in the same way, spectral line diagram also, gap is decreasing. Remember, for this direction, frequency increasing. How we can tell that? Now students, you know that, very easy. Now you know that when the electron is transferring from the first energy level to the fifth principal energy level, the energy gap is 100 to 1900. What is the difference? The difference is 1800. The difference is 1800. Right? Now look at the second transition. Energies, first principal energy level to fourth principal energy level. What is the gap? 100 to 1800. Then what is the difference? 1700. Very easy, right? We calculated the energy using equal H nu neither. Same energy. Because we know that one, if the electron is moving from the high energy level, it should absorb the energy. That's what happened here, right? Now let's go for the first principal energy level to the third principal energy level. What is the gap? 100 to 1500. Then the gap will be 1400. On 1400. Now look at this one. N equal 1 to n equal 2. What is the gap? Gap is 100 to 1000. Gap is 900. Look at this one. I told you the spectral lines in the spectral line diagrams are representing the energy gap between the energy level. Right? Energy. Don't misunderstand. These are not energy levels. In the energy level diagram only we can see the energy levels. But the spectral line diagram, these lines are representing the corresponding energy gap. නිකමට හිතන්න මේක නිකන් amount එකක්, quantity එකක්. Just imagine this is a quantity. This line is representing a quantity. What is that quantity? Energy gap between the energy levels, not the energy levels. Right? Can you see me? Gap is decreasing. 900, 1400, 1700, 1800. Gap is decreasing. 500 gap, 300 gap, 100 gap. Understood? So that energy levels gap is also decreasing in the same way. Therefore, spectral line diagram also representing that gap is decreasing. So try to understand, students. This is the corresponding energy. This 1800 is the corresponding energy that is required to move for the fifth principal energy level. We can calculate that one using equal h nu, right? Therefore, now tell me all of you, for which direction frequency is high? To which direction frequency increases? Left to right or right to left? Frequency increases for which direction? Left to right or right to left? Sarina, correct. Good. Opeshani, correct. Lakshmi, correct. Correct. Very good. Very good. Can you understand? This is the ultimate truth. If you can understand this one, emission spectrum, absorption spectrums are nothing. මේක තේරෙනවා නම් හරියට මේ මොකක්ද කිව්වේ කියලා වැඩේ ගේමක් නෑ. පට්ටම ලේසි. Right? This is what happened. Most of the students can't understand what are these lines. These lines are representing the energy gap between the energy levels. Right? We know that one, when an electron is moving for high energy level, that electron should absorb the energy. That absorbed energy is denoted as a line in the spectral line diagram. That's all. Nothing is there. Dark lines on a bright background. Dark lines are missing energy levels, energies. Missing energies. Missing energies means that hydrogen is absorbing the amount of energy that is equal to this one. So that is denoted as a line. That's all. HRI. Understood? See how easy this one. Right? Therefore, we can tell that frequency and the energy increases for this direction. For this direction, frequency and energy increase. Frequency and energy increase. Right? Can you understand? Right. Now let's go for your doubts. Put all your doubts. I will explain this one again. All I want is you won't understand this one. You must understand this one. That's enough for me. And what are the doubts you have? So why gaps are varying? So does each line representing individual hydrogen atom? No, that's not individual hydrogen atom. These are the possibilities. Are the gap considered the energy levels? No. That, sir, does each line represent individual hydrogen atom? No, not individual hydrogen atom. So how could we analyze and come to the conclusion of range of transition electrons just by observing lines? So how could we analyze and come to the conclusion of range of transition of electrons just by observing lines? Can understand that one. Why? So how could we analyze and come to the conclusion of range of transition of electrons just by observing lines? So this is a practical experiment. This is a practical experiment. Using this practical experiment only we can analyze the lines, right? Otherwise we don't have any option to observe the lines. Okay, how the Madhurukshan, yeah. And Gimani, sir, why the different size spaces between them? Different sizes between the energy level means energy level gap is decreasing according to the Bohr diagram. So this is a Bohr's postulate. Okay, when the number of protons are increasing, electrons are closer to the electrons are becoming closest to the nucleus. So therefore, energy gap is decreasing. Always this is the way energy gap. So horizontal gap become vertical gap. No, we can't tell like that. But horizontal gap, vertical gap, both are same. The gap is same. Is that mean frequency increases with wavelength decreases? Yeah. When the frequency increases, wavelength decreases. That's correct. Exactly correct. And sir, do the dark lines get darker from left to right because high energy absorption? So do the dark lines get darker from left to right? Dark lines get darker. Dark lines get darker. No, that is depending on the number of hydrogen atoms in the sample. That means that depending on the electron transitions, we can't tell like that which one is becoming more darker. In that way around, we have to think that n equal 1, n equal 2 should be the darker one. N equal 1 to n equal, because this is the possible electron transition always. So the gaps varies in the spectral line due to the difference of energy. Yeah, that's correct. So are the dark lines show the absorbed energy frequency? Yeah, dark lines are representing the absorbed energy, right? Dark lines are representing the absorbed energy. Exactly. Anything else? Anything else? Good, right? Okay, crystal clear. Okay, good. Raise your hand who understood this one. Raise your hand who understood this. Quickly. Right. Okay. Now, first homework. Palavini homework, right? Other than homework here. You have to draw the atomic absorption spectrum, energy level diagram, and the spectral line diagram both together in a page, right? What is it? You have to draw the corresponding energy level diagram and the spectral line diagram for the atomic absorption spectrum in the same page. Both, right? Both of them in the same page in this way, like I drew. And you have to clearly draw that one and send the answers for the WhatsApp group. And in the same way, we are going to draw this one for the emission spectrum also. For today, we are going to discuss that one. You have to do that one, okay? Now, in the tutorial, I have given you space in the page number 33. After the paragraph we wrote, I have given you small space there. In that space, you have to draw only this spectral line diagram. Antimata dila tin dang space එකේ අඳින්න spectral line diagram එක විතරයි. Don't draw the energy level diagram. Understood? In the tutorial, don't draw this diagram, energy level diagram. Only draw the spectral line diagram, right? And write down frequency, energy increases, lambda wavelength decreases. Quickly draw it. If you want, you can take a screenshot, photograph, doesn't matter, right? Of E, this is new. New means frequency. A symbol, this is the symbol that we are denoting frequency. New, Greek letter, new. So I drew the energy level diagram before already, together already. Okay, right. It's okay, Lakshmi. Doesn't matter. Do you have enough space to draw both of them? I thought that you don't have time, space there. See how easy these things, neither. We explain the practical using the theory that we learned. How that spectral lines are obtained. That means electrons are transferring between energy levels. Those energy gaps denoted in a diagram in this way. That's all. Done. Eh? Right. So this is all about the absorption spectrum. Shall we go for the emission spectrum quickly? Done. Others quickly. Shall I erase this one? Are you done? Your other. Okay, done. Right. Right. Now let's go for the, without wasting time, let's go for the emission spectrum. Emission spectrum is easy. Right opposite of this one, right? Make a money pattern. Right? Opposite of this one. Nothing else. Here we put the arrow towards upward. In the next diagram, we are going to put the arrow to downwards. That's all. Right. First of all, let's discuss about the practical, right? As before. So our topic is today, now the next one, atomic emission spectrum. Atomic emission spectrum. Right. Now look at this one. Here also we have a kind of a practical like this. right? So this is sensitive screen again. Let's see how we can, what kind of a spectral line diagram we have here, right? And as usual, here we have using prism because we can see the energy radiations properly by keeping a gap using a prism. And this one, this is voltage energy source. So this is actually a voltage energy source. And this is hydrogen atoms. In this chamber, we have hydrogen atoms, kind of a chamber, right? Connected to this source. And this chamber is emitting some radiations in this way. It's emitting some energy radiations. And that is gathered okay. And here you can see, so this is the sensitive screen. Bright lines in a dark background. Okay. Here, if we want, we can write down 4 lines because, yeah, here we can draw 4 lines. That is possible because bright lines only 4. There are more than 4, but I have taken here only 4, right? Just imagine there are more, but I have taken only 4 lines for my analysis, right? Right. Now, okay. Now look at this diagram. This is also same kind of a diagram like absorption spectrum, but the only difference here is emission, atomic emission spectrum. Remember, students, now we are going to analyze the emission spectrum, not the absorption spectrum. Earlier, we analyzed absorption spectrum. Now, here we have hydrogen sample. We are supplying high voltage source energy. So what will happen? Hydrogen atoms will absorb the energy. Okay, now okay, we know about that one. And after absorbing the energy, we know that one, these electrons are moving for the high energy levels. We analyze that one in the absorption spectrum. But these electrons, when going for the high energy levels, those electrons went for the high energy levels. Again, they should come back for the low energy levels, right? Those who went for the high energy levels, definitely they have to come back for the low energy levels again. So when they are coming back to the low energy levels again, what will happen? They will release the energy. Those release energy radiations, we collected, we gathered that one, and we analyzed that one through a prism. Thus, those energy radiations sent through the prism, and we analyzed that one in the sensitive screen. So in that sensitive screen, we can see bright lines in a dark background. Bright lines in a dark background. In the absorption spectrum, you saw there are dark lines in bright background. Here we have bright lines in a dark background. What is the reason? Here we are analyzing the emission spectrum, right? We are letting absorb energy to the hydrogen atoms, and then later we are wait until the energy released from those hydrogen atoms. Those energy collected, and we analyze that one. So these are what? Emission radiation. Understood? So this is the emitted radiations. Earlier we analyze absorb radiations. Here we are analyzing the emitted radiations from the hydrogen. Hydrogen is emitting the radiations when the hydrogen atom coming back again for the lower energy levels. So that radiations collected and went through a prism, and through the prism we collected those radiations into a sensitive screen, and when I'm analyzing that sensitive screen, I can see bright lines in a dark background. I can see bright lines in a dark background. Remember students, these bright lines are representing the emitted radiations. What happened to the dark background? Dark background is representing already absorbed radiations from the hydrogen. I told you, since we are supplying high voltage source, high energy, definitely hydrogen is absorbing the energy. Hydrogen is absorbed energy. That means all the energy absorbed by the hydrogen. So we cannot have radiations here. So therefore sensitive screen should be dark. But here we wait until those electrons, some of the electrons are releasing energy and coming back to the lower energy level, then they will release the energy. Those energy radiations collected and went through a prism, and we got that one into a sensitive screen, and we analyze, we observed some bright lines in a dark background. This is known as what? Emission spectrum. Can you understand the difference between absorption spectrum and the emission spectrum? What are the doubts you have? Let's see. Sir, can explain the initial step again, please? So what caused the bright dark lines difference in both the spectrum? Right. Remember, in the initial step, what we have done here is we have used high voltage source. We are using high voltage source to give the energy for hydrogen atoms. When we give energy for the hydrogen atoms, what will happen? Hydrogen will absorb the energy and they will go for the high energy levels. According to the Niels Bohr diagram, can you remember I told you that when the electrons are moving back to the energy levels from high energy levels to low energy level, they will release energy. They will release energy as electromagnetic radiations. So we have hydrogen sample here, which is containing electrons in high energy level. They absorb energy, and now they are in high energy level. At a particular time, some of the hydrogen atoms are coming back to the lower energy level by releasing energy. By releasing energy, they will come back again. So those emitted radiations, they are now here. Those emitted radiations can be collected, and we can analyze that one. That is emission spectrum. Emission spectrum. That means emitted radiations means radiations up there. So therefore bright lines we can see. What happened to the dark background? Bright always the term bright representing energy radiations are there. Dark means always not the presence of energy radiations. Bright means sensitive screen, bright means always energy radiations are there. The sensitive screen always dark means no energy radiations. So these are the emitted radiations. That's why we can see them in bright lines. Dark background is representing the energy radiations already absorbed by the hydrogen atom. Understood? Right? Lashmi and who asked me that doubt? Opeshani. So how we collect and connect the hydrogen in circuit, right? So that is not our business actually. Why? So we can use many methods to connect that one. This is a chamber. So we can have the positive and negative tips and we can connect that one in the, that's a practical scenario. We don't have to worry about that one. And how we collected the energy radiations. So that is actually not our business. We have so many methods. So I'm not going to discuss about them here. So you can search that one, right? So I'm only discussing about the chemistry that we have to learn. Okay, Nuha? Don't worry about that one. And the next thing. So, sir, if we wait the absorption experiment, would you the again release energy? Yeah. They will release the energy. They will release the energy again. Right? If we have to obtain the absorption spectrum, we can analyze the same emission spectrum also. Because same atom, same hydrogen atoms, right? So what is the barrier between emitted rays and prism to reduce the radiations? Please, between the emitted radiations and prism, what is the barrier between the? Yeah. So actually, this is not kind of a barrier. This is kind of a what? Energy. This is a radiation collector. That means we can what? We can collect the radiations. There are some instruments. We can collect the energy radiations, and we can what? We can what kind of compression, and we are going to what use a high voltage beam. That means this is kind of a radiation beam. Now these radiations are separated everywhere. So these are radiations clustered everywhere and spread everywhere. So using an instrument, we can collect those radiations into a particular small range. Understood? So here actually we have an instrument. So we don't have to worry about that one. I just mentioned you here, these energy radiations we collected, and again that converted into a radiation beam in this way and went through a prism, and we took that one on the sensitive screen, right? That's not kind of a barrier. We are collecting the radiations through that one. And Sinetma, okay, never. So then can we say that there are more energy radiations in hydrogen emission spectrum since the bright area is greater than the emission spectrum? So then can we say that there are more energy radiations hydrogen emission spectrum since the bright area is greater than the there can be more radiations, right? Exactly, we can tell. So what causes to discontinue the radiation in between source and prism? This is not discontinuous, right? This is not the discontinuous. These are the radiations emitted by the hydrogen atom. As I mentioned you, we are using instrument to collect these energy radiations, and that energy radiations are what may release as a sharp beam. That's what happened here. Okay, that's not kind of a barrier for discontinuing that energy radiation, not like that. Same energy radiations, we collected that one as a sharp energy beam. That means energy radiations are coming in this way, and we have instrument here, and those energy radiations are going in this way and going a sharp beam. That's all. Right? Anything else? Any doubts? Raise your hand who understood this explanation for the emission spectrum. Very easy. Quickly. Okay, good. And if you have any doubts, please put your doubts in the chat box, right? Okay, now quickly draw the diagram. And these are the emitted radiation beam. Right, quickly draw this diagram in the page number 33. Last of the page, I have given you this space. Quickly draw this one. And others, if you have doubts, please put your doubts in the chat box. Okay, Inuji, after a long time, dark lines absorb, bright lines emit. Yeah, exactly. That's what happened. Simply, short and sweet. Inuji, correct. Dark lines means absorb, means we can't see them. Okay. So this is the emission spectrum. That's also discontinuous, right? Because only few radiations are emitted. Okay, because few electrons are coming back to the low energy levels. Let's draw the same diagram for the emission spectrum also as we draw for the absorption spectrum. So can we find continuous spectrum in visible light also? Visible light is continuous spectrum. Visible light is continuous spectrum. Senura, visible light is a continuous spectrum. Students, when you ask O-level results are coming? Don't know. What is the date they have announced? When they will release the result? Before A-level start the exam. Okay. A-level date has announced as November 27th or something. That means you have to wait until November. In November, we will be at second unit and third unit. In September, I will finish first unit. Last year, yeah. So what is quantum chemistry? Quantum chemistry means quantum chemistry. How we can how I can give you simple explanation for this one. Quantum. I'll tell you in this way. Now we have learned that in the Bohr diagram, energy levels are there. The electrons are located in energy levels. In the quantum chemistry, they are telling that around the atomic nucleus, there is a cloud of electrons, particular area. in that area only electrons are located. Okay. So quanta means quanta. The term quanta means basic particle of anything. Now, if I take universe, what is the quanta of universe? Atom. Quanta of universe is atom. All of the things are made by atoms. So basic particle in matter is electron. We learned that one. I'm talking about the universe. Everything is atom. And if I take quanta particle of water is water molecule. What is the quantum particle of energy? Photon. That is the quantum particle of photon. Actually, Max Planck only the idea represented. That means he's the one who found these quantum chemistry theories, the main concept, and other scientists developed that one. In the quantum chemistry, we have to learn a lot of mathematical concepts. Okay, according to the quantum chemistry, actually, the things that we are learning here is not real. That's completely different. Quantum chemistry is there, quantum physics is there. So everything is actually kind of what particulate likewise. So the main concept is everything is kind of particulate. Energy, even energy. Energy also having a particle, photon. So a lot of mathematical concepts are there in quantum chemistry, right? That's very difficult to describe. We have to discuss quantum numbers, right? In our first unit, we are learning quantum numbers. Under the quantum numbers, I'll again explain what is actually quantum. Quanta. Actually, the term is quanta. Quanta converted quantum, right? In university also, we have to learn about quantum chemistry, right? Okay, right. Done with drawing? Are we done? Shall I erase this one? Are we done? Please respond me. Yes, done. Right, okay. Now, in the given paragraph in the page number 33, I have given you space right down there. I'm going to erase the diagram. When energy supplied to hydrogen atoms, they absorb energy and move to high energy levels. The spectrum at which the same energy, the spectrum at which the same energy is emitted at particular time is called emission spectrum, right? So hydrogen atom absorb the energy, they go for the high energy levels, and they are coming back again for the lower energy levels. Then they will release the energy. Those release energy can be analyzed as the emission spectrum. Okay. Quickly write down. Right. Now let's go for the page number 33. In the page number 33, they have given that the resulting atomic emission spectrum is a discrete line spectrum with bright lines on a dark background. Students, highlight that term, bright lines, in your tutorial, page number 34. Page number 34, they have given the first statement. The resulting atomic emission spectrum is a discrete line spectrum with bright lines on a dark background. So you know that one, bright lines are representing the emitted energy radiations, and the dark background is representing the absorbed energy, that means missing radiations absorbed by the hydrogen atoms. Bright lines on dark background, right? Okay, right now. Bright lines, PRIGs. Now again, I'm going to draw the diagram for the same diagram for the absorption spectrum. Let's see. Third principal energy level. Fourth principal energy level. Okay, right. N equal 1, N equal 2, N equal 3, N equal 4, N equal 5. This is energy level diagram. And this is spectral line diagram. Okay, right. Now, same as before, we know that one, we had these kind of lines neither. In this way, right? So now these are bright lines on dark background. Right? We know that, students, remember, this is emission spectrum. Electrons are emitting energy. At which instance electrons are emitting energy? මොන වගේ වෙලාවද electrons energy එක release කරන්නේ? Electrons are moving from high energy level to low energy level, right? Earlier in the absorption spectrum, we learned that electrons are moving from first energy level to high energy levels, from low energy level to high energy levels. Now, these electrons are coming back to the low energy level from high energy level. So this is emission spectrum, releasing energy. Now look at, this is the first spectral line you can see from the right hand side. So this spectral line is representing that electron is moving from n equal 5 to n equal 1. This is the corresponding electron transition. N equal 1, n equal 5 to n equal 1. Understood? N equal 5 to n equal 1. And this second spectral line representing the electron transition from n equal 4 to n equal 1. See how easy these things are. N equal 4 to n equal 1. This third spectral line representing that electron transition between n equal 3 to n equal 1. N equal 3 to n equal 1. Sir, why always first principal energy level? Can't it be second principal energy level? We are going to learn that one in the hydrogen emission spectrum. Lyman series, Balmer series, Paschen series, Brackett series, Spun series. These series are obtained by considering the energy level. When the electrons are falling for the first principal energy level, we call that one as Lyman series. For the second principal energy level, that is known as Balmer. For the third one, Paschen, Brackett, Fun, Humphrey, likewise we can go. Understood? Right. So let's learn that one later. First of all, look at this one. Now, according to my spectral line diagram, this is the last line. That means electron transition from n equal 2 to n equal 1. Can you understand? Electron transition from n equal 5 to n equal 1. You can see that this is the right opposite of the previous one, right? In the previous absorption spectrum, we consider that n equal 1 to n equal 5. Now here, opposite, only direction, n equal 5 to n equal 1. And here, n equal 5 to n equal 1, the corresponding spectral line. Second one is n equal 4 to n equal 1. So this is also n equal 4 to n equal 1. Right? What about this one? This is n equal 3 to n equal 1. This is n equal 2 to n equal 1. Very easy. Look at this one. Right? So this is n equal 3 to n equal 1. N equal 2 to n equal 1. Understood? Corresponding electron transition. So as same before, we can consider that energy, corresponding energy here is 100 kilojoules, and here 1000 kilojoules, and here 1500, and here 1800, and this is 1900. So always keep that in mind when the electron transition is taking place between two energy levels. Always that release energy or absorb energy, either release energy or absorb energy, that is equal to the energy gap between two corresponding energy levels. So what is the energy gap? 1900 and 100. What is the energy gap? 1800. That energy gap is represented by this spectral line, and here 1800 to 100. So the energy gap is 1700. Look at this one, n equal 3 to n equal 1. Energy gap is 1500 to 100. So that is 1400. And the energy gap between n equal 2 to n equal 1, so the energy gap is 900. Can you understand? So that's why energy gap is decreasing. So actually the spectral line diagram also representing that energy levels are decreasing. In the same way, spectral lines also decreasing the energy because these energy gaps are decreasing. So the only difference between, look at this one, if you can understand this one now, then ඔයගොල්ලන්ට මේක තේරෙන්න ඕනේ absorption spectrum එක emission spectrum එකයි කියලා කියන දෙකක් නෙමෙයි. එකම තමයි. අරකෙම ප්‍රතිවිරුද්ධ කෙනානේ. So you have to understand that absorption spectrum, emission spectrum, both are not different. Same thing, but two different instances. Understood? Two different occasions, two different incidents in the same thing. Same hydrogen atom sample, same energies, but only the difference is in the first one we analyzed absorption. That means electrons went to the high energy levels. In the emission spectrum we analyzing, electrons are coming back to the low energy levels. That's what happened. Very easy. Can you understand? Raise your hand who understood this difference. Please understand, raise your hand who understood this quickly. All of you, all of you. There are 30 people in the session, 29 people. Okay, good, good, good. Right. Yeah, Lakshmi, there are more possible electron transitions. Exactly. There are more possible transitions, right? That's what we are going to learn under the hydrogen emission spectrum. This is only the electron transition up to the first principal energy level. There can be more electron transitions. Why can't electron move for the second principal energy levels? From 5 to 2, 4 to 2, 3 to 2. Why these electrons can't stop at second principal energy level? It can be, right? So there are so many possibilities. Right? So now only we just learn the concept. First of all, learn the concept, we'll do absorption spectrum, emission spectrum. If you can understand the concept, we can go further, right? Right, okay. Amshi, you asked me to repeat the difference between the emission and absorption. Very easy. In the previous one, absorption, that means we learn electrons are moving from low energy level to high energy level. Now here, electrons are moving from high energy level to low energy level. So they will release the energy. They will release the same amount of energy. Right? Now you can understand that energy absorbed from n equal 1 to, when the electron transferring from n equal 1 to n equal 5, it is absorbing the energy. That was 1800. And the same electron coming back to the previous energy level, that means first principal energy level, then they will, then it will release the same amount of energy, 1800. That means you can understand emission spectrum and absorption spectrum. Both the spectral lines are coincide each other, same values. Let's discuss that one later, right? Right, okay. First of all, you have to understand this one. Now, in the given space, page number 34, after the first statement, write down, draw the only spectral line diagram. Draw only the spectral line diagram. So then these bright lines are exactly placed in previous dark lines location. Exactly. You understood that one. You can place these bright lines in the previous absorption spectrum, spectral line diagram, then you can coincide them. That means this one fill the gap. Understood? At there you obtain dark lines neither. Senura, very good. Very good. These bright lines can paste there. You can fill the gap. That's what happening. Very good. So this is understanding, right? See, this is the understanding. After explaining everything, you can understand what's happening there. Right? Very easy. If you can't understand this one, don't worry, right? I believe all of you can understand. I know that one. But if you can't understand this one further, don't think that much. We can easily go for the questions, right? Don't worry. And you can watch again the recording. And if you have any doubts, you can ask me. Don't think that much serious. Godak serious gan depa. Right. Sir, this is the wavelength increasing here. Yeah. Here, for which direction frequency, wavelength, frequency and energy increases? Same way. For this direction, energy gap is increasing. Opeshani. Energy and the frequency increases in the same way. They increase. But what about the wavelength? Wavelength is inversely proportional. So therefore, wavelength lambda decreases. Understood? Same way. Energy and the frequency increase, wavelength decrease from left to right. So do we need, what is it? So do we need to draw this one also as a homework? Yeah, exactly. Gimani. Wow, homework so what you have to do is, again, you have to do this one again as a homework. What you have to do? Homework, as before, you have to draw the energy level diagram, spectral line diagram, both together for the emission spectrum, and you have to send that one to the WhatsApp group. Right? මම notice කරන් ඉන්නේ homework කරන කට්ටිය සහ නැති කට්ටිය. හරි? මම දන්නවා කවුද හැමදාම homework කරලා ඉවන්නේ නැත්te කවුද කියලා මම දන්නවා. homework කරන් නැති කට්ටියට මට කියන්න තියෙන්නේ ඔයගලන්ට exam එකට ගියාම තේරෙයි මොකද්ද වෙන්නේ කියලා. හරි? Those who are not doing homework, I want to remind you that you will understand what will happen to you when you go for the examination. So be careful. I don't have time to check each and every homework separately, right? So so therefore, but I have noticed who are the people every day uploading the note per May homework to the WhatsApp group. Wait, you will face for the consequences by yourself at the examination, right? After the first unit finishes, I will keep online examination, right? You have to turn on camera and I'm going to keep an online examination. So let's see what will happen, right? We are going to prove that everything is possible in the online also, not only in the physical, right? That is our concept. We have sent you the tutorials. All the tutors, all the teachers are sending the tutorials, right? Mudita sir, Tarindu sir, Niroshan sir, everyone is sending the tutorials. Me also sending the tutorials. right? Everyone is providing recordings and everything. We are going to give you the homeworks. So examination will also be there, right? We will prove that everything is possible in the online classes also, right? Because world is changing, we have to go with the trend. Sir, can we finish the first minute before the school start? Yeah, exactly. I'm going to finish the first minute before school start, for sure. School are starting after November again. Before, after November, or before November. Anyway, in the September, end of the September, I will finish the first unit. And October, we are going to start second unit and third unit. Okay, are we done? Mudita sir said it could be January sir when school start. Then January means we can complete the second unit, I think, right? If it is January, very good. That means we are actually far away from the school, so therefore. But in school, don't worry, they will finish the first unit within 2 days, 3 days. They can finish that one. They have that much capability. Okay, don't worry. School teachers la සතියෙන් දෙකකින් ඉවර කරන්න. සතියේ දෙක atomic structure සතියේ දෙකයි. පොඩ ඉස්කෝලේ ගිහලා බලන්නකො මේ explanation එක compare කරලා බලන්න හරි. Yeah, flash. Flash, exactly. Flash Pro Max. Right, okay. Shall I erase this one? Are we done? Right, okay. Now go for the tutorial, page number 34. The absorption and emission spectra of an atom, which are line spectra, conclude that the electrons are located at energy levels around the nucleus of an atom. Stress, this is the summary. This is the summary. Remember, this emission spectrum, absorption spectrum, both of them are representing that. Both of it representing that these electrons are located in energy levels, right? Spectrum analysis is actually practical scenario. This is a practical. This is kind of a practical that we are not doing at school. That's why we are learning this one as a theory. This theory is simple. Doing practical is difficult. That's why most of the schools are not conducting this experiment. May experiment කරන එක lazy නෑ school. Understood? So that's why we are going to discuss the theory behind this practical. After discussing this theory, hydrogen emission spectrum, the main part in our syllabus, will be easy. Now, I believe that you understood, according to this experiment and the theory that we learned regarding the emission spectrum, the absorption spectrum, these electrons are moving from low energy level to high energy level. They will absorb the energy. And in the spectrum line diagram, we can see that corresponding energy gap between this electron transition. And again, these electrons, those electrons went for the high energy level, coming back again for the low energy levels, and they will release the energy. Those release energy again denoted as a spectral line in the emission spectrum. So the final summary is electrons are going here and there between the energy levels. Energy level concept is completely true. We can accept that one. Energy level කියන concept එක හරි. Niels Bohr was true. according to the hydrogen emission spectrum. From the theory, from the practical that we learn up to now, we can understand that why these kind of spectral lines are obtained, because energy levels are existing. The electrons behavior in between energy levels is possible. Understood? Hydrogen emission spectrum proves Niels Bohr energy level concept. That's the final summary. Understood? What is the final summary? Emission spectrum, absorption spectrum, completely spectrum analysis proves Niels Bohr energy level concept. That's why we obtain this kind of spectrum, right? Highlight that one in the tutorial. The absorption and emission spectra of an atom, which are line spectra, these are not continuous, right? Conclude that electrons are located at energy levels around the nucleus of an atom. Highlight that one quickly. Highlight that. And then I have given that in brackets, a line does not represent energy levels. Very important, because most of the students are thinking that these lines are representing energy levels. But my students, they know these are not energy levels. These are the energy gap between these energy levels, corresponding energy gap that is denoted as a line. Our students know it. Right? Therefore, take out your red pen, continue from there. There is small space near. After that statement, after that sentence, you have small space there. So continue that one in this way. Let's write down what does mean by exactly this line. Write down. Take out a red pen and write down. A line represents, a spectral line represents, a spectral lines represent the energy gap between two corresponding energy levels. A line represents the energy gap between two corresponding energy levels. That's all. A line represents the energy gap between two corresponding energy levels. Right. Now, you know the main difference between the absorption spectrum and the emission spectrum. Absorption spectrum is obtained when the electrons are moving for the high energy level. Emission spectrum is obtained when the electrons are moving back to the low energy level. That's the main difference. Now let's analyze what is the main similarity. What is the main similarity between the emission spectrum and the absorption spectrum? Look at this one. Now, I'm going to draw the spectral line diagram of both emission spectrum and absorption spectrum together. Right? I'm going to draw emission spectrum diagram, absorption spectrum diagram, both together. Right? Look at this one. dark lines on bright background. Bright lines on a dark background, isn't it? So this is the emission spectrum and the absorption spectrum. Now let's see how my students are, right? Now I'm going to give you a chance to prove that you all are my students, right? I'm putting chance at the Ogolanda, Ogolo, mugging Igana Michael, right? Let's see how you are going to use. Shall you use that one? Pulon Dolan program. Can you prove that you are my student? Huh? Okay, right. What is the main similarity in between the absorption spectrum and the emission spectrum? Put your answers in the chat box. Hi, no one is there. Why? Oh, okay. We're getting the answers. Frequency, okay, interest in the spectrum, energy, difference in energy level, the gap. Corresponding lines are same. Energy gap. Yeah. Energy gap. Okay, good. Right, okay. Yeah. Okay, right, okay. Right, okay. You have proven that you are my students, right? Very good. Remember, students, actually, as I mentioned you that this is the corresponding energy line. This is the corresponding energy line. If I consider this one in the absorption spectrum, this is n equal 1 to n equal 5. And this is the energy level, energy electron transition form, n equal 5 to n equal 1. N equal 1 to n equal 5, n equal 5 to n equal 1. What is the common factor? The same two energy levels. Energy gap is same. That means the amount of release energy is equal to the amount of absorbed energy. When the electron is moving from first principal energy level to fifth principal energy, the absorbed amount of energy is, just imagine, 1800. The same amount of energy we release by the electron transition form n equal 5 to n equal 1. Energy gap is same. These lines are representing, these spectral lines are representing the corresponding energy gap, and the energy gap is same. The release amount of energy is equal to the release amount of energy is equal to the absorbed amount of energy. Since energy is equal, you know that according to the equal h nu equation, frequency is also equal, because h is a Planck's constant. So therefore, this is directly proportional to the frequency. Frequency and the energy, corresponding energy gap of these two spectral lines are similar. Can you understand? Can you understand what happened? The corresponding energy gap and the frequency in both diagrams are similar. Dark lines are representing that absorbed energy. That same energy, absorbed energy, will release when that electron is release energy from the electron transition 5 to 1. May 5 to 1, 1 to 5. Energy both are same. 1 to 5, 5 to 1. Both are same. So the common factor, the main similarity is what? Frequency or the energy gap. Very easy. See how is this? So this is actually n equal, second one, we can write down this is actually n equal 1 to n equal, second one, n equal 4 to n equal 1. And this is third one, n equal 1 to n equal 3. N equals 3 to n equal 1. Same energy. This is n equal 1 to 2. N equal, sorry, here we can consider 6 to 1. Here 5, 4, and here 3. Okay. And here 5, 4, n equal 3 to n equal 1. N equal 2 to n equal 1, and n equal 1 to n equal 2. See how easy these things? Very easy. Energy gap is same. The main similarity is energy gap same. Right? As I mentioned you, remember always keep that in your mind. For this direct, sorry. For this direction, always energy frequency increases. Energy frequency increase. Wavelength lambda decreases. Right? So remember students, and the next thing is, since the frequency are similar, we can see that now listen to this one, very important, right? Now, these are dark lines, neither. These are dark lines in the bright background, and these are bright lines on dark background. So I'm going to remove these dark lines in this way. I'm going to remove them. I'm going to remove this dark line. Okay. Look at this one. I'm going to remove this dark line. When I took that one. Now I'm going to keep that one here. Is that exactly fit to that diagram? Is that exactly fit to that diagram? Yes or no? Yeah, exactly fit. Because same frequency. I'm going to remove this one, this bright line, and I'm going to keep that one here. That line is exactly fit on this diagram. In the same way, this one, again, this one. This one, I'm take same frequency, right? Same frequency. This one, take and paste here. This one, take and paste here. So what will happen? This diagram will be completely bright background. That means, students, this is the same diagrams for the hydrogen. This is the same diagram that we obtain in two occasions. Absorption and emissions. If you get together, if you combine this absorption spectrum and emission spectrum together, you will have continuous or discontinuous. What do you think? Is that continuous or discontinuous? Continuous. Very good. Continuous spectrum. Because here you can see that in the absorption spectrum, 4 lines are missing. Those 4 lines can be observing the emission spectrum. Understood? So these lines, if I take this one and if I take this diagram and full diagram, and if I paste this one here, what will happen? Definitely you can see the continuous spectrum. Completely bright background, you will see that. So that's why we are telling these two diagrams together we can consider it's a continuous diagram. Because this missing line in the absorption spectrum can be again seen in emission spectrum. Missing line n equal 1 to n equal 5 in the absorption spectrum can be seen again in the emission spectrum. Here again, this one here, this one, this one, this one, this one. So that means if you combine these together, you can obtain the continuous spectrum. Continuous spectrum. Right? Can you understand what did I say? Please raise your hand who understood that. Please raise your hand who understood that. Please raise your hand who understood. Good. Very good. There are 30 people raised hand. Very good. Right? Very easy, ne? Can you understand? Very easy. Emission spectrum and the absorption spectrum. Yeah, what are the doubts now you have? This is so interesting, sir. Yeah. So that is Sandeep, sir, right? That is me. Sir, should the hydrogen amount be equal for this to be combined? No. Not hydrogen amount. That should not be equal, but the number of transitions should be equal. Mushab, understood? Number of transitions should be equal, Mushab, not the hydrogen atoms, because these are represented transitions. Right. Anything else? Let's go for the chat box. Yeah, crystal clear. Okay, good. Very good. Any doubts? Anything else? Do you want to ask any doubts from me? Right. Okay. Now let's go for the tutorial. Next paragraph in the page number 34. When the atomic absorption spectrum and the atomic emission spectrum of the same element are obtained, the frequencies of the dark lines of the atomic absorption spectrum and the bright lines of the atomic emission spectrum are exactly the same. Yeah, as I mentioned you, they are same. So that's why we can consider this one as a continuous spectrum together, right? Therefore, even these two spectra are taken separately. These are discrete line spectra. If we taken this one as separately, we can consider this one is discontinuous. But when they are synchronized means we are going to consider them together, coincident. A continuous spectrum is obtained, right? If you consider these two together, we can obtain a continuous one. Okay, right. Now I have given you space. Quickly draw this diagram. Quickly, yeah. In the given space, quickly draw this diagram. Oh my God. Time has passed. I thought to start hydrogen emission spectrum. Anyway, quickly draw this one. Michel, hi. So is the maximum number of energy level is 6. In the first one is mentioned n equals 6 to 1. Yeah, that means n equals 6 to 1 means there can be maximum number of energy level is 6. Yeah, that's correct. Then if the number of energy levels are 6, we can obtain 5 spectral lines. If it is 7, we can obtain 6 of spectral lines likewise. Quickly complete the diagram. Draw it nicely, huh? Lasan ganna. Done, eh? Are we done? Shall I erase this one? Quickly draw this one. Quickly, yeah. Are we done? Right, okay. You all are very good, huh? Because when I'm starting the session today, there were 32 people. Now in the session, there are 30 people. Only two has left. Only two have left. Others are still in the session. I'm really happy about you, right? I believe that you are really interesting in this topic. Right, okay. I'm going to erase this one. We have to write, we have to explain this one. Shall I? Okay. If you can't write down this one quickly, take a photograph or screenshot. Later you can complete the note. Right. Now let's write down the note for this one. In the next page, I have given you enough space to explain this one. Let's write down that one quickly. The Bohr's theory explained the similarities and the differences of the atomic absorption emission spectra. Okay, done. And let's write down quickly. Consider write down. Consider the atomic absorption. Turn to the page number 35. I have given you space. Write down this quickly. Consider the atomic absorption and emission spectrums of the same element. Actually, we have taken here hydrogen. When an electron at a lower energy level is energized it moves to high energy level to a high energy level. It moves to high energy level by absorbing a certain amount of energy. Certain amount of energy. That energy is recorded. That energy is recorded as a dark line, as a dark line, as a dark line in the spectral line diagram. When the same electron, write down, when the same electron come back again to the lower energy level, it releases energy. It releases energy and that energy recorded as is recorded as bright line in a dark background. Dark background. I have written that one as bullet wise. So you can complete the note in the page number 35 quickly, no doubt. By consider the atomic absorption and emission spectrums of the same element, hydrogen. When an electron at a lower energy level is energized, it moves to high energy level by absorbing a certain amount of energy, and the energy recorded as a dark line in the spectral diagram. When the same electron come back again to the low energy level, that will release energy. That energy is recorded as a bright line in a dark background. Right, okay. Quickly complete this. Done. Okay, done with writing. Okay, students. Now, so this is the end of the today's session. Actually, we have discussed emission spectrum and absorption spectrum. First of all, raise your hand. Tell me whether you understood this. Please raise your hand. Good. Right. Okay. Good. Very good. If you have any doubts, put your doubts in the chat box. If you have any doubts, put your doubts in the chat box. And the homework is, what is the homework? I gave you that. Spectral line diagram and the energy level diagram and the spectral line diagram, both for the absorption spectrum. You have to draw that one and do that one. And again, for the emission spectrum also, spectral line diagram, energy level diagram, both draw them together and write down. So draw that one together nicely and put your drawings in the WhatsApp group, and I can see you up all the drawings. Okay, so do that one, very small homework, right? Very easy thing. So that's the thing, right? So if there is any update, I'll let you know through the WhatsApp group. Okay. Yeah, these two questions, right? And one more thing, don't forget that soon after the class, please go for the WhatsApp group and send me a feedback message, whether it is good or bad, right? Doesn't matter. About the today's session, your thoughts, feedback. I need a feedback. Okay, please do that one. So now I will finish the session. After the session, you can go to the group and quickly send me a message, feedback message. Okay, neither, right? Right. If you have any doubts, put your doubts in the chat box. Let's see. And others, you can leave. Let's meet on next Saturday. Until then, bye bye. Have fun. Good night. If you have any doubts, stay and ask your doubts. Okay. God bless you. Bye. Good night. Senura, I'll discuss this question number 45 and 48 in the question discussion session. I will let you know about that one. Supipi, you didn't get the class. Supipi, you are the today is the first day. Okay, send me a message and I'll ask Ms. Sandhuni to add you to the group, and you can ask the payments from the Sandhuni. Okay, Supipi, send me a message. Okay, right. Okay. Then I'm going to end the session, right? Okay. Bye. Good night.